This is MSJ Chem. In this video, I'll be looking at oxidation states. The oxidation state is the hypothetical charge an atom would have if the bonds in a compound are assumed to be 100% ionic with no covalent character. Oxidation states are written with a plus or minus first, followed by the number. So that's +2, not 2 plus. Oxidation is defined as an increase in oxidation state, and reduction is defined as a decrease in oxidation state. For example, in this reaction, zinc reacts with aqueous copper sulfate to form aqueous zinc sulfate and copper. The oxidation state of the zinc is 0, and the oxidation state of the copper in copper sulfate is +2. The oxidation state of the zinc in zinc sulfate is +2, and the oxidation state of the copper is 0. So the oxidation state of the zinc has increased from 0 to +2, which is oxidation, and the oxidation state of the copper in copper sulfate has decreased from +2 to 0, which is reduction. So next, we look at the rules of how to assign oxidation states. So we'll start with elements. Elements have an oxidation state of 0. So some examples of elements are copper, iron, bromine, chlorine, and oxygen. Next, we look at oxygen. Oxygen in a compound has an oxidation state of -2, except in peroxides when it is -1. So for example, in carbon dioxide, the carbon has an oxidation state of +4 and the oxygen -2. In H2O, the hydrogen has an oxidation state of +1 and the oxygen -2. But in hydrogen peroxide, the hydrogen has an oxidation state of +1 and the oxygen has an oxidation state of -1. Next is hydrogen. Hydrogen in a compound has an oxidation state of +1 except in metal hydrides when it is -1. So in the previous examples we looked at, hydrogen has an oxidation state of +1. However, in sodium hydride, the sodium has an oxidation state of +1 and the hydrogen has an oxidation state of -1. Group 1 and Group 2 elements in compounds have oxidation states of +1 and +2 respectively. So sodium has an oxidation state of +1 and magnesium would have an oxidation state of +2. Fluorine in compounds always has an oxidation state of -1. The remaining Group 17 elements, that's chlorine, bromine, iodine, and astatine, can have variable oxidation states. So chlorine can have an oxidation state in compounds of -1 to +7. Bromine can have oxidation states in compounds of -1, +1, +3, +5, and +7. For iodine, it can be -1, +1, +3, +5, +6, and +7. And for astatine, we have -1, +1, +3, +5, and +7. Next, we look at the oxidation states of the first row D block elements, from scandium to zinc. So as you can see from this table, with the exception of scandium, nickel, and zinc, the remaining elements all have variable oxidation states. For example, vanadium can have an oxidation state in compounds of +2, +3, +4, or +5. And manganese in compounds can have an oxidation state of +2, +3, +4, +6, or +7. The sum of the oxidation states in a neutral compound is equal to 0. So here we have CH4, methane, which is a neutral compound. The carbon has an oxidation state of -4 and the hydrogen an oxidation state of +1. Overall, the sum of the oxidation states is 0. Another example is NH3 ammonia. The nitrogen has an oxidation state of -3 and the hydrogen +1. Once again, the sum of the oxidation states is equal to 0. The sum of the oxidation states in a polyatomic ion is equal to the charge on the ion. So here we have an example, which is the sulfate ion, SO4 2-. We have 4 oxygen atoms, each with an oxidation state of -2. This gives us a total of -8. To give an overall charge of 2-, the oxidation state of the sulfur is +6. In ionic compounds, the oxidation state of each species is the same as the charge on the ion. So for example, sodium chloride is composed of positive sodium ions and negative chloride ions. The charge on the sodium ion is 1 plus, the charge on the chloride ion is 1 negative. So the oxidation state of sodium is +1, and the oxidation state of the chlorine is -1. For covalent compounds, assume that the more electronegative atom has a negative oxidation state, and the less electronegative atom has a positive oxidation state. So here we have CCl4, which is carbon tetrachloride. Chlorine is more electronegative than carbon, therefore we assign it the negative oxidation state. Next we look at oxidation numbers. Oxidation numbers are represented by a Roman numeral. The terms oxidation number and oxidation state are sometimes used interchangeably. So here we have some examples. Cu2O is copper 1 oxide. The 1 in brackets tells us the oxidation number of the copper, which is +1. Here we have CuO, which is copper 2 oxide. The 2 in brackets tells us the oxidation number of the copper, which is +2. At the bottom we have iron 2 chloride and iron 3 chloride. The difference being the oxidation number of the iron, which is +2 in iron 2 chloride and +3 in iron 3 chloride. So next we look at a couple of examples. Deduce the oxidation state of sulfur in H2SO4, which is sulfuric acid. Well, we know that hydrogen has an oxidation state of +1 and oxygen has an oxidation state of -2. That gives us a total of +2 for the 2 hydrogens and -8 for the 4 oxygens. There's no charge on the compound, therefore the oxidation state of the sulfur must be +6. Our next example is deduce the oxidation state of chromium in potassium dichromate. So potassium is a group 1 metal, therefore it has an oxidation state of +1, and the oxygen has an oxidation state of -2. That gives us a total of the +2 for the potassium and -14 for the oxygen. There is no charge on the compound, therefore the oxidation state of the chromium must be +6. This is because there are 2 chromium atoms in the compound. The name of the compound is potassium dichromate with a Roman numeral 6 in brackets. This tells us the oxidation state or the oxidation number of the chromium, which is +6.